Hi, this video will cover section 4.5, which is graphs of sine and cosine functions. And this is for the class Math 2412. The objectives for this lesson will be to sketch the graphs of the basic sine and cosine functions. Also, for those functions, we're going to have to define terms such as the amplitude, also the period. And with that, that will help us sketch the graphs of sine and cosine functions. We are only going to focus on those two functions today. And we're going to graph, of course, the parent functions first, but then we're going to move on and extend that concept into translations of the graphs. And so if you remember from Math 13-14, in chapter 1, section 1.6, you cover some of those translations. And so those include reflections, shifting, horizontal shifting, vertical shifting, and also stretching vertically or horizontally. And so I hope that with the examples that we cover here and also in the lab session, I could help you out I can help you remember all of those translations, but if you need a little refresher, I do have a video on my YouTube channel, and it will be section 1.6, translations of graphs, something titled like that. Okay, finally, our last objective will be to use those graphs, the sine and cosine functions, to model real life data, and with that answer some questions. And those type of real life applications could include like the water level going up and down in the ocean, for example. Okay, so let's go ahead and get started. So in the figure that you see here, we have the sine function. And I'm going to go ahead and add that on both ends, we could have arrows. And that is because the domain of a sine function, it is actually all real numbers. So from negative infinity to positive infinity. However, what is here not gray but in black, that is, I'm going to go ahead and highlight it for you. That represents one period of the function. So when we were looking at the unit circle, one period or 2 pi radians, which is one full revolution, that was, well, I already said it, one full rotation, that was 2 pi. And for the next, for the one you see here, it's like if you were to unwind the circle and then place it like that because of the sine values. So for example, here at, if we are speaking about degrees, or let's do radians. Actually, every time we graph this, even on your calculator, you have to change the mode to radians. It's very important. So in this case, at 0 radians, we know that the sine value, the sine of 0 is equal to 0. And so we could see that represented here by the X-intercept. Now, if we move on to, let's say, here, which is pi over 2, the sine value for pi over 2, remember, is the y-coordinate. And so the coordinates at this point happen to be 0, 1. So because of that, the sine of pi over 2 is equal to 1. And you could see that represented here and is in fact, now if the input was pi over 2, the output will be 1. And that is the point that we see here. In fact, that will be considered a maximum point. Now let's move on to the next quadrant angle, and that will be pi radians. So for that one, the point here with respect to the unit circle, it is -1, 0. So for the sine value of pi, it is equal to 0, the y value. So it's that point right here. Okay, moving on, we're going to look at what happens here at this point, which is representing the angle 3 pi over 2. And so the coordinates with respect to the unit circle of that point will be 0, -1. Now, remember, we need the y coordinates, so the sine of 3 pi over 2, it is equal to the y coordinate of that point, which is -1. And we could see that point represented here. And in fact, we could label it as the minimum. I don't know why it's not writing. Here we go. So minimum point. It has the lowest y value, the smallest. Okay, and if we complete a full circle, then we will get we will come here to 2 pi radians. And so the coordinates of that point are 1, 0. And so again, to find the sine of 2 pi, we need to look at the y coordinate. If we're looking at the unit circle, that happens to be 0. So that is the sine value of 2 pi. And so that will be located here on the y-intercept. So from here, we could see 1, 2, 3, 4, 5 key points. So I'm going to show you on the next slides how we will find those 5 key points if we were not graphing just the parent function. By the way, this is what we call the parent function of the sine function, and the equation for it will be y equals sine x. So previously with the unit circle, we were talking, our input was the angle measure, whether it was in degrees or radians, and our output was either the sine value or the cosine value. I'm sorry, yes, sine or cosine value. Now with this graph, our input is the angle measure as well, and the output is only the y value, and that's it. So for the domain, our angle could be any real number, but for the range, and you could see here, if you consider the minimum, I should call it that, the minimum and the maximum point for the range, our values are going to go from -1, that will be the smallest, to +1. The 5 key points, I'm going to list them here. 5 key points. We're going to have for the sine function, we're going to have 3 X-intercepts. And then we're going to have 1 maximum, which is here. And we're going to have 1 minimum. Now let's go over the parent function of the cosine function. And remember, parent function will be that function in its simplest form. And so that will be the equation that you see here, y equals cosine x. So your input, it is the angle, the degree measure, the angle measure in radians. And it is also all real numbers, so from -infinity to +infinity. And the range is going to be the same as the sine function. The smallest y value will be -1, and the largest will be +1. I use the square bracket because that means they are included in our interval. So let's go ahead and draw the unit circle here. And let's go ahead and plot our points that are on the x and y axis. So I'm going to start with 1, 0. The next one is 0, 1. We have -1, 0. And then we have 0, comma, negative 1. Now, for this question, or for this trigonometric function, we're going to be focusing on the x coordinate because we are answering the questions for cosine. So let's go ahead and write them here. So not sine, but cosine. So the cosine of 0 radians, it's going to be the x value at that particular point, which is 1. And we can see that here. So when the angle measure is 0, the y value, and I know this is kind of weird. So when we're talking about the unit circle, we call it the x value. So let me just call it input and output. So when the input is 0 radians, the cosine value or the output will be 1, which is what we see here. And that is actually going to be our maximum point. Well, one of those. Then let's move on to the cosine of pi over 2. And if I look at the number at the coordinate that I have highlighted, that is equal to 0. So if the input is pi over 2 radians, the output is going to be 0. So that's going to become an x-intercept. Then if we keep moving in the counterclockwise direction, the cosine of pi is going to be negative 1. Then let's move on to the cosine of 3 pi over 2, and that is going to be the coordinate that I highlighted, which is 0. And if we go one complete turn, one full rotation or one full revolution, the cosine of 2 pi is going to equal to 1, positive 1. And that is what we see here at this point. And I forgot to graph to point it out to you, which was the 3 pi over 2, which is also an x-intercept. So let's go ahead and list them. We're going to have 3 x-intercepts. No, not 3. In this case, we're having 2. Sorry. So 2 x-intercepts. And those are the points that are on the x-axis. And they occur at pi over 2 and 3 pi over 2. Also, we're going to have one maximum point and we're going to have one minimum point. So this function, the cosine function, only one period, one rotation of a circle. If we were to unwind that circle, it will be placed like that. So it kind of looks like a parabola, but still it reaches a maximum and then it decreases again. But one cycle is only what I have highlighted. But it's important to mention again that since the domain is all real numbers, we do have arrows at the end because the function keeps going and going, and it is the domain, because the domain is all real numbers. So I have said it several times, the domain of the sine and cosine functions, it is the set of all real numbers. And we already went over how the range for each of them, it is the interval -1 to 1. And that one full period, which is what we highlighted, here's for the cosine, and here is for the sine function. One full period, it is 2 pi radians, like a one full rotation of the circle or one revolution. So I'm going to move on to the next slide again. And if you look at the graphs, actually, let me just leave them like that. The sine curve is symmetric with respect to the origin. How do I know that? Well, because this function, let's say for this particular point, the input was pi over 2, and the output was 1. So if we look at the point that it is reflected across the origin, the point will have the coordinates negative pi over 2 and the negative 1. And I forgot to mention, but we do graph, since the domain is all real numbers, we do consider negative angle measurements, and that's why you see on the left side of the y-axis, you see the negative pi over 2 or negative pi, negative 3 pi over 2. So this is what makes a function graphically, that's what it makes it be symmetric with respect to the origin. And also, because that function, just to refresh your mind with 13 from the class 13-14, we check to see if a function is odd by replacing the x value or the input with negative x. And after doing that, what we obtain with respect to the original function will be the complete opposite. So in this case, with sine functions, if we look at what is the sine of pi over 2, that is equal to positive 1. So if I was to replace the input with negative pi over 2, the answer, and I'm going to show you the graph again, it is what we have here as negative 1. And so what that tells me is that after replacing pi over 2 with negative pi over 2, it does satisfy the definition of odd functions. We got the complete opposite of the positive pi over 2, of the sine of pi over 2. So when a function is odd, we say that they are symmetric with respect to the origin. That's what odd functions do. Now, if we look at the cosine function, and let's go ahead and look at the graph and just focus on this part here. From here, from here to here. And so let's go ahead and take the point. Let's use pi. So cosine of pi, we could see it here. It has the value of negative 1. And if we look here on the left side of the y-axis, cosine of negative pi is going to have the value of negative 1 as well. And so this is a case where the output is the same whether the angle is positive or negative. It's the same angle but with opposite signs, but the output for cosine is still negative 1 for both. So let's see how that compares to even functions. So for even functions, the general rule is that if you replace the input with the opposite, meaning opposite sign, then you will obtain the output of the original variable or angle or number as the positive one. So here we try with cosine of negative pi. The answer was negative 1 is here. And it is equal to the cosine of positive pi, which is negative 1. So Well, actually, this is just not written properly, so this should say cosine of positive pi. And so in both instances, the answer is -1. So it satisfies this equation, and we do say that they are even. And so functions that are even, they happen to be symmetric with respect to the y-axis. And that is because it's kind of like the parabola, where they, if you were to fold it across the y-axis, if you were to fold this graph across the y-axis, which is here, you will obtain the same on the right side of the y-axis and the left side of the y-axis. They will completely overlap. Let's review the basic sine and cosine curves or graphs. So on the left, we have the sine graph, and on your right side, we have the cosine graph. And these are the graphs for the functions. Well, we can see the equation here. Y equals cosine of x, and here we have y equals sine of x. So for both graphs, both functions, we are going to have the same inputs. So the domain is all real numbers for both of them. And the range is going to be from -1 to 1, and all the numbers in between, which are fractions. Same for both graphs. Okay, so now let's talk more or reinforce the 5 key points. So intercepts. The x-intercepts for sine function will occur here at 0 radians, at pi radians, and at 2 pi radians. And then they will keep repeating, because remember, the domain is all real numbers. So either we go on the left or right direction, we will have the same curve. Now for the cosine graph, the x-intercepts are at pi over 2 and at 3 pi over 2. Now let's talk about the maximum points. Sine function has 2, at pi over 2 and at 3 pi over 2. Oops, my bad, that should be a minimum. So it has 1. Sine graph has only 1, sorry. Where the cosine parent function has 2. One that occurs at 0 radians and also at 2 pi radians. And it will keep repeating every 2 pi because that's the period. So I could tell you it will happen again at 4 pi, at 6 pi, and if we go in the negative direction, it will be happening at -2 pi, -4 pi, and every 2 pi radians. Now, finally, we have the minimum points, and those are the points for which the y value is -1, because that's the smallest. And sine function has 1, occurs at 3 pi over 2. So that was an Amber Alert. And okay, so minimum points, that's what we were talking about. So it occurs at 3 pi over 2, but the minimum value is -1. And with the cosine graph, we have a minimum right here, and it occurs at pi, but the actual minimum value is -1. Similarly with the maximums, the maximum value is +1, but it occurs at pi over 2 for sine, and for cosine, the maximum value, the maximum output is 1, but it occurs at 0 radians and 2 pi radians. Now I'm going to add a little bit to our parent functions. We had already discussed that the period is equal to 2 pi. That is the 1 revolution of the circle, and if we were to unwind that circle, it will cover the distance that you see from here to here. For cosine, it would be like that, what I'm tracing with pink. So that's why the period is 2 pi. Now, let's talk about another word called amplitude. And the amplitude, it's what we consider half of the distance between the minimum and the maximum. And so if you were to count the distance from 0 to y equals 1, it would be 1. And then from y equals 0 to negative 1, it would also be 1. And so it is that distance, which is 2, but divided by 2. So it will be given by the absolute value of the max minus, and remember those are the y values, and then divided by 2. So in this case, our amplitude is equal to a 1. And that is because I'm sorry, not minus, but plus. It's 2 over 2, which is equal to 1. Also, because our equation doesn't have a visible coefficient, so we know there's an implied 1 right here, that also tells you what the amplitude will be. And for our next example, we're asked to graph the sine function, but what we're doing now is changing the amplitude from a 1 to a 2. And we know that because that little coefficient of the sine function, you have a 2 in front of it, so that is always going to tell you what the amplitude will be. Now, the period will be the exact same thing. It will be 2 pi. And so let's try to do this. So let's actually write down what the amplitude will be. So the amplitude is equal to 2. Okay, so what this means is that from our parent function, we're going to have to graph something that will be extending a little more on the vertical direction. So it's actually considered to be a vertical stretch. So I'm going to just make my y-axis longer. And let's go ahead and mark. If this is 1, then 2 will be approximately here. And also in the negative direction, this is negative 1. So let's move on to negative 2. Okay. So let's do this. What we're going to do first is find those 5 key points. From the parent function, the 5 key points for sine were 3 x-intercepts. And I want to do something with you guys. So if we know that they are x-intercepts, to be more exact, so for every single x-intercept, the y coordinate, it's going to be 0. But first, well, let's do that here. So let's write that down. It will be 0 for the y because they are on the x-axis, meaning that the point did not move up or down. So the y coordinate is 0. Now for the x value, that is going to be 0 and 2 pi. Now to find the one in the middle, we're going to use 0 plus 2 pi. So we're going to find the midpoint. We're going to add them, like the average, and divide them by 2. And so this is going to give me 2 pi divided by 2, which is equal to pi. And that's how we know here is the value for that. However, our problem is not really asking us to graph it in that for that particular period. And what they're asking us to do, or for that segment of x values, what they want us to do is graph it on this interval here from negative pi to 4 pi. So then what we're going to do is extend it a little bit more, or let's just leave it like this, and then we will just extend it after. So let's keep doing what we're doing. All right, now we're going to go ahead and try to find the coordinates for the maximum point. Now, the maximum point is going to have a y value not of 1, but of 2, like that. And so that point will occur here. How do I know it's there? Well, because that maximum is going to be exactly halfway between the first two intercepts, the one on the left and the one on the middle. So I can say 0, I'm going to take the average to find the middle point. And I know this one is easy, but once we have horizontal shiftings, you might have to actually calculate the midpoints by hand to be more precise. So in this case, it would be like 0 plus pi divided by 2, and we know it's going to be pi over 2. So that will be the x coordinate here. Okay, so that will be the maximum. Now for the minimum, the y value is going to equal to negative 2. How do we know that? Because the amplitude is a 2. Remember that came from this number here. So also we could say that the range is going to be from negative 2 to positive 1, because this 2 here is stretching the parent function vertically. So it's pulling that maximum from 1 to 2 and that minimum from negative 1 to negative 2. So where does that happen? Well, it's going to happen exactly at the midpoint of the second and the third x-intercept. That's how we find those midpoints. So it's going to be halfway between that intercept and that intercept. So we could say pi plus 2 pi and then divide by 2. So here we add the two numbers on the numerator, so that will be 3 pi, and then divided by 2. We prefer fractions over decimals, so 3 pi over 2 is located here. So then the minimum will have the y value of negative 2 and the x value of 3 pi over 2. Now that I have those key points, I'm going to go ahead and trace a curve. And let's use a different color. Let's see. Let's use this light blue. So I start from the origin, then I go to the maximum, then I go back down to the x-intercept, and then I go to the minimum, and then I go back up to the intercept. And of course, it's not a very nice curve, so we could just make the line thicker. Now, just to be in compliance with the question, they want us to graph this from negative pi. So from here to, I believe, 4 pi. So what I'm going to do is extend my x-axis. So then let's see. I'm going to say this is 3 pi. And then right here it will be not 2, but 4 pi. Okay, so we're going to keep extending the line, and remember that the same pattern is going to repeat. So then I'm going to start from on the left side of the y-axis. So from the origin, I'm going to go down to another minimum point, which will occur right here at negative pi over 2 and negative 2. That's the point. And so I'm going to connect my graph, and then I'm going to go back up to right here, which will be an x-intercept, and that point will have the coordinates negative pi, comma, 0. So we go back up there. Now, we're just going to stop here because that's what the instructions of the problem was telling us to do. So now I'm going to go on the right direction of my first period that I graphed. And so what comes after a minimum and an x-intercept, it will be a maximum. So it will be right here. And then we will have another x-intercept at 3 pi. Then we will have a minimum, and if you don't know exactly what this is, the x value or the angle, we could take the midpoint of 3 pi plus 4 pi and divide it by 2. And so that will actually be 7 pi over 2. So, and that will have the y value of negative 2. So 7 pi over 2 and the y value negative 2. And then, of course, we have another x-intercept right here at 4 pi. Okay, and of course, you are always welcome to check your work with the calculator before you submit your homework or for your exams. Remember, you need to get a graphing calculator as soon as possible. The calculators you could download for free on your laptop or tablet or phone. And you could also go to desmos.com. I mentioned that on my I believe maybe on the Blackboard intro to Blackboard video. So let me write here the word of the name of the website, Desmos, and that you could also use it on your phone, and you can graph trigonometric functions as well. So for the rest of the section, we will study the graphic effect of each of the constants, and we're going to use the constants A. A is for amplitude. Then we are going to have B, and B is going to be telling us the period, how the period will change. Remember, for the parent function is 2 pi. Also, we will have what is C over here for the constant. Remember, these constants are representing real numbers. So those will be telling us the vertical stretch. I will write that down in a minute. And then finally, we will have the constant D, and that will be telling us the vertical stretch. So let's just write all of them down. So A is going to be in fact, the absolute value of A, it will be the amplitude. What will happen if we had something like negative 2, y equals negative 2 sine of x? Well, it will be also with an amplitude of 2, but it will be a reflection of the graph that we have here. So meaning that instead of starting at the origin and then going to a maximum point, we will do the opposite. So we will start at the origin and then go to a point down here at negative 2. That is if the equation had a negative 2 in front of sine. But the amplitude is always the absolute value because we're talking about distance. And so that's why I say absolute value of A. So that will be the amplitude. Then we do have B, which is going to help us with period. And in fact, to get the period, we are going to use 2 pi over B. Then we move on to the letter C. And so for the letter C, and that will give us the horizontal shift or translation. And then finally, we have the letter D. And the letter D is going to be representing the vertical shifting. So it's going to tell us if the graph is going to move up or down or stay the same, kind of like symmetric with respect to the, well, no, not really. It will not be correct for me to say it that way. But with those key points being on the x-axis, let's just say that. Okay, now if we have a constant that it is greater than 1 and we're using the absolute value, so even if you have like the graph that the equation I wrote down here, even if you were to have this equation, the amplitude, it's still the absolute value of 2, which will be positive 2. So, and if that's the case, that the absolute value is greater than 1, and then you actually have a stretch, and it's actually a vertical stretch. And if the constant is less than 1, whether it's positive or negative, because we're using absolute value. Let me give you an example. Let's pretend you have a function like 0.5 cosine x. So we know 0.5, it is a number less than 1. And for that reason, the graph will be a vertical shrunk, because sometimes some books call it a vertical compression. We already discussed the amplitude and the period, but let's just highlight a few things here. So for the amplitude, you look at this number and it will tell you that your range is going to be between the negative and the positive of that same number. But then the amplitude will be the absolute value of A. That is what your amplitude is. Don't forget that. Oh, well, we have it here. And we also have it here. And recall that it is the same for sine and for cosine. So we look at that constant in front of it, and then that's what we will be using. For the next example, we're going to be graphing a reflection, or going over a reflection, because we already have the graph here. So let me walk you through the graphs first. So a reflection across the x-axis is something that you don't need to write this that I'm about to write, but please pay attention. If you had a point here, and this point had the coordinates, let's say 1, 2, and I tell you I want you to reflect that point across the x-axis. So the point will be here. The x-coordinate is still the same, but the y-coordinate is the one that changes. So whenever we do a reflection across the x-axis, the sign that changes from positive to negative or from negative to positive, it will be the y value or the output. And that's why you see here from 2 to negative 2. So having said that, we're going to use that concept to graph a reflection across the x-axis, and we know it will be that because it has a negative 2. So let's look at, and yes, I have the cosine graph here. So for the parent function of cosine, remember and this is very useful. You could start to find your 5 key points. You can start by locating your 2 maximums, and those will typically occur at 0 radians and at 2 pi radians. There we have them. The maximum value is a positive 1, so that's why we have 2 pi comma 1, and we have 2 pi, I'm sorry, that should be a 0. 0, comma 1. Then the midpoint between those two is going to be our minimum. And the coordinates for that will be pi. Right here we have pi. And the minimum value is -1. Remember, this is the parent function of the cosine function. Now, to find the x-intercepts, we could find the minimum point between the max and the min. And you could see clearly that is going to be here at pi over 2. Then our fifth key point, it's going to occur right here between pi and 2 pi. And so that will be happening at 3 pi over 2. And the point is right here. So let me just write the coordinates for that. Here we'll have 3 pi over 2 comma 0 because it's an x-intercept. And then here we have pi over 2 comma 0 because it's also an x-intercept. Now that is just one period of the parent function for cosine right here, one period by itself. Now let's move on. What if instead of having an amplitude of 1, our graph had an amplitude of a +3? So that's what we have here. And let's just use that one. Actually, let's keep it here. So it will follow the same shape as the previous one. And you could see that here. I'm going to trace it. It looks gray. I'm going to trace it with pink. And it will be that. So let's look at it. Now the maximum points are here at 0, 3 and at 2 pi, 3. Oh, this is 0, 3. The other one should be 2 pi, 3. There we go. Now we do have that minimum point, and it is still occurring at pi, but it's gonna be pi, -3 because the amplitude is changing to 3, meaning that the range will be from -3 to +3. And we use square brackets because they're included. Now the x-intercepts, those are easy because they're just gonna be the same y values. So when you have a vertical stretch, the x-intercepts don't really change. And so what I'm about to trace with the highlighter in pink is that graph again. And there we have it. Now, what we're trying to graph is a reflection across the x-axis. So the difference is going to be this little -3 here. And so what we're going to do there is we're going to reflect every point across the x-axis, meaning that the y coordinate will change from positive to negative or from negative to positive. So let's start with the points that were the max here and here. So those are going to be now minimums. So they go from being minimums to being maximums. So I'm going to go ahead and erase that yellow highlighter. Oops, I just erased everything. That's fine. And then the x-intercepts will stay where they were. But now what's going to change is what used to be our minimum here, now it's going to be reflected up here. So the coordinates for that one will be pi, 3. And for our minimums will be 0, -3. That's what we used to have. And then for the other, it will be at 2 pi comma negative 3. Okay, so I'm going to go ahead and erase this. Now I'm going to trace that one with a purple highlighter. And so that will be from here, it goes up. So instead of starting at a maximum point for cosine, it starts at a minimum point. So it increases, and then it goes down, it decreases, and then it goes back up, increases. And we could see the same behavior in the other direction. So reviewing what period is, for a parent sine or cosine function, we consider the period to be 2 pi because that is what one full rotation is equivalent to. So we consider the space that it will, like the graph from 0 to 2 pi, that would be one full period. Now, whenever we do have a number, and remember we were looking at all those, we were using A, B, C, so B determines the period, and more specifically, it's going to be the ratio of 2 pi over B. And we will see some examples. And then just as a review again, the A represents the amplitude. Don't forget that. Okay, so similarly, when B is greater than 1, the period, remember B is and it's kind of like a constant that will be multiplying your x. And so it will be affecting all your x values directly. And what's going to happen is that you will be dividing those values by whatever the constant b is equal to. So if that constant is greater than 1, since you are dividing your angles or your angle measurements, you're going to be obtaining a horizontal shrinking. On the other hand, if that constant b is, and we should probably just say absolute value is less than 1, then you will be obtaining a horizontal stretching. And when we relate this type of graphs to real life problems, most of the time the x-axis, it could be not most of the time, but an example could be like time. And so imagine if you have a number here and you have 2 pi divided by that number, so that is going to affect the time in which the wave, the sine or cosine waves, go up and down. So they could go either faster, that will be the horizontal shrinking. It will go from looking like a graph like that. It could look like a graph with a horizontal shrinking. It could look like this. Okay, not very pretty. And with the horizontal stretching, we could have something like that. So if it was related to time, it will take more time. Okay, now we're gonna add more identities to our collection of identities. So we already discussed how the sine function is odd. It is odd, and it does satisfy the equation f of negative x equals negative f of x. So because it is odd, we're going to use this identity as in we could replace one for the other, just like that. So if you had something like sine of negative 3 pi over 2, we could just replace it by the sine of 3 pi over 2, but with the opposite sign in front of it. Okay, so for cosine again, it is even, and it satisfies the equation f of negative x is equal to f of x. So for example, if you had the cosine of negative 5 pi over 4, that will be the exact same as cosine of the same angle, but positive, like that, of 5 pi over 4. So we could use that identity to help ourselves and replace things to make them simpler. So of course, cosine of negative x, you could just use cosine of x to rewrite. Remember, identities are used to rewrite functions. Now let's move on to our third constant, which is c, and that one is what's telling us how the horizontal translation or horizontal shift will occur. So this could be moving the parent function to the left or to the right. Now for the sine function, we were looking at a graph that looks like that. And so we had the starting point, that's what I would like to call it. The starting point is equal to 0, or yeah, with respect to the angle measurement. And the ending point for the parent function, it is 2 pi. So because of that, we will take what's inside the parentheses, the whatever's the coefficient of the angle measurement, or of x, and also the phase shift, the plus or minus c, and we will make two separate equations where one will equal to 0 and the other one will equal to 2 pi. And that's how it will tell us if our graph, instead of starting like the original one, perhaps it will start here and then complete a one period like that. So that is what we refer to as the phase shift. Now, if your b value, this one here, is not a 1, of course, when you solve your equation, you're going to end up with some sort of fractions. So for example, if I have bx minus c equals 0, and I want to solve for x, this will be x is equal to positive c over b. And that is what we have right here. So x will be between that. And then if I take the second equation, which is bx minus c equals 2 pi, and I want to solve for x, it will be bx is equal to 2 pi plus c, and then we divide by b, so we will have 2 pi plus c, everything divided by b. And that is what we see here. So here they're calling them left and right endpoints. You know, same thing, starting point, ending point. So that's what we call phase shift, just to use it again. And if the question, to review the name, if the question on web assign is something like, what is the phase shift? All you have to answer is take those two constants from your function, which is b and c, and then you will make a ratio of c over b, just like we see it here on this part. So we have already covered three things. We cover the amplitude, which is given by the constant a, amplitude. We already covered the period, which is given by the constant b right here. And then we also covered the phase shift, which tells us how we move to the left and to the right. So what we're gonna do now is graph one of those equations, and we could see that we have everything here. So we start with amplitude, which is coming from this number 3, negative 3 in fact, but the amplitude is the absolute value of negative 3, which is positive 3. Because of that, the range of this equation is going to consist of the interval negative 3 to positive 3, with those two numbers still included. Now let's go ahead and figure out the period. The constant that is here next to the x is 2 pi. So that's why we're taking the original 2 pi and dividing it by 2 pi. So that is going to give us a 1. That would be the period. It is kind of weird, I know, but it's like we're going to be graphing something. Instead of labeling our x-axis by pi, 0, pi over 2, pi, 3 pi over 2, 2 pi, and so on, we would just simply say this is 0 and this is 1. What? Well, 1 radian. By solving, then we got to find the phase shift, and so that is given by taking what's inside the parentheses and solving these two equations. One will equal to 0 and the other one to 2 pi, because that's what the parent function does. So if we solve this equation here, remember we're trying to solve for x, so x is going to equal, or 2 pi x will equal to negative 4 pi. Okay, we're still trying to solve for x, and 2 pi, it happens to be multiplying to x, so if we move the 2 pi across, it's going to be dividing, so negative 4 pi divided by 2 pi, and this will give us x is equal to negative, we cancel the pi, and we will have negative 4 over 2, which is negative 2. Okay, that's going to be our starting point. So if I was to extend this x-axis, let's say that negative 1 is here, and then negative 2 is here. So right here. Okay, now for the other equation, we are going to solve it. So 2 pi x is going to be equal to 2 pi. We take this positive 4 pi, subtract it on both sides or move it across, and that will give us negative 2 pi. We have 2 pi here, x, and we're gonna divide by 2 pi, so here negative 2 pi divided by positive 2 pi, and that will give us x is equal to negative 1. Okay, so let's say negative 1 will be here, and so what it means is that from that interval that we're being asked, where will be one of the periods based on the phase shift with respect to the parent function. The starting point will be here at negative 2, and the ending point will be here at 1. So from here to here, we're going to have a complete cosine period. And also, it's important to notice that this is a negative 3. Okay, so just as a rough, quick sketch of the parent cosine function, remember we used to start at 2 maximums, and then from there we will find a minimum, and then from there we will find the 2 x-intercepts, and that's what will use to give us that shape. Well, ours is not only shifted horizontally, but it's also reflected across the x-axis, because the equation has a negative 3 here. The a value is negative 3. That tells me that it is a reflection. So instead of looking that way, we use the reasoning that it's going to be when things are reflected, if there was no horizontal shifting, we will just simply start at the minimum points, then we will have the midpoint to make it a max, and then the x-intercepts will still be there. And then, of course, we will connect it like that. That will be one period. Of course, ours is going to start more towards the left. So with that said, we're going to take the solutions that we got from that equation. So we got here negative 2. Instead of starting at 0, we start at negative 2 for the x-axis, and we end at negative 1. And we already established that those 2 points will be minimum points. And so they will be here and here. And of course, we know that the minimum value in question is negative 3, because if the amplitude is 3, the range is going to be from -3 to 3. So -3, of course, will be the minimum. We have it here. And then 3 will be the maximum. So the maximum is going to be in between the two minimum numbers. How will we find that x-coordinate? We know the maximum will be 3, +3. But the x-coordinate is going to be the midpoint between -2. So we're going to add them. -2 plus -1, and then we're going to divide by 2. So when you add two negative numbers, you keep them negative, so it's -3/2, or -1.5. So let's say -3/2. And so that maximum, the maximum, remember, is the y value, but it happens right here. Well, that's where the point B will be, and the x value for that one, it is actually 3/2. Negative. I should say that. -3/2. 3/2. Okay. Then after that, we move on to find our x-intercepts. And so to find those x-intercepts, I'm going to make some more room here. So to find those x-intercepts, we're going to take the midpoint between these two x values. So we're going to use -2 plus -3/2 and divide that by 2. So -2 in terms of halves will be -4/2. And then we have -3/2. And then we're dividing all of that by 2. So if we add two negative numbers, remember they will remain negative, so that will be -7/2. And then we divide that by 2, 2/1. So here you can think of this. If you have a half and you divide it again by 2, you will end up with a quarter. So that would be the case for this one, but we could also know that if you multiply the outer quantities, that will be -7 times 1 will be -7. And the inner quantities, 2 times 2 will be 4. So that is the x value that we will need here, -7/4. We're talking about an x-intercept, so by default the y-coordinate is a 0. Now let's find the other x-intercept. So we're going to take this x value with that x value. So I'm going to make some more room here. And for that particular one, we will do -3/2 plus -1 and divide that by 2. So this will equal to -3/2. -1 in halves will be -2/2. We divide that by 2, and that will give me -5/2 divided by 2, and that will equal to -5/4. So that will be our value here, and this will be a 0. And so I'm going to just zoom in here and write them down for you. So here the x value happens to be -7/4, and the one here, the x value happens to be -5/4. And the y value, it is 0 because they are on the x-intercept. So to graph one period of this graph, it will go from here to here. And if we are asked to graph more than one period, then we will just repeat that same pattern to as many periods as they want us to graph. The final type of transformation is the vertical translation, and that will tell you if the graph is moving up or down, and that is given by that constant that is just being added or subtracted to your whole trigonometric function. And so therefore it will affect your y value. The y value will be added or subtracted. And what would happen, and we use this word oscillates because as you can already see, our graphs move like that. They go up and down. And so what happens here is that when we don't have a vertical translation, the graph oscillates in with respect to the x-axis or to the line y equals 0. But when we have a number different than 0 here, then our graph will oscillate. Let's pretend this is D just to stand for a number, and so the graph will oscillate with respect to that line. So it will go like that. And or if the D value was down here, then our graph will oscillate with respect to that line that we see here, that we see there. So the x-intercepts will of course change. For example 7, we have the table is showing the depths in feet of the water at the end of dock at various times during the morning, where t equals 0. Now, instead of using x for our independent variable or input, we're using t for time. And we have on the graph is showing us times from 0 to 12. And then the y value or the output will be the depth of the water in the dock. Since our day starts at midnight, yes, at 12 a.m., that is actually being considered the starting point at t equals 0. So this will be like the hour 0, which corresponds to 12 a.m. So based on that, we're going to use that information, and we're going to construct the equation or the trigonometric model. So let's see, if we look at our table or at our graph, we could see that the maximum y value here is going to be 11.3. And we have, which is representing this point, well, the y value of it, and the minimum y value is actually here. It almost looks like a 0, but if we look at the graph, we could see that is 0.1. So we're going to use those two for us to get the minimum and the maximum, and once we get that average, we will be finding the amplitude. And I did discuss this at the beginning of the section. So let's see. A, which is the amplitude, is going to equal to 1/2 . So I already have the answer written down here. So I substituted the maximum, 11.3, minus the minimum, which is 0.1, divided by 2, or multiplied by 1/2 is the same thing. And what I get there is 5.6. So this is going to represent the amplitude. Now we have to find the period. I use the, and I'm going to go back to the graph. So if we look at the table, the x values for which the maximum and those are at 10 and at 4. So I'm going to use a different color. So 10 and 4, those are the ones that correspond to the maximum and to the minimum. And I'm going to use those. 10 minus 4, and then I'm gonna multiply it by 2, and then that will give me 12, because 10 minus 4 is 6, times 2, it will be 12. Now, to find the midpoint between the minimum and the maximum, and remember that is, what do we need it for? Well, because we need to see where our graph will be reflected. And you could see the answer here is 5.7. So that is going to be that kind of like that midline for the one that your graph will be oscillating with respect to. So that will be 5.7. Why do we add and divide by 2 or multiply by 1/2? Because we're finding the average between the maximum and the minimum. For amplitude, it was actually the difference, because we are finding the amplitude, yeah, half of the distance between the minimum and the maximum. So this is half of the distance, amplitude, and for the midline, we use the average of the maximum and the minimum. Okay, so I'm gonna pause here for a second. Okay, so what I found out is that here the letter P is a little confusing, misleading, because it is not the period. What it's actually representing is B, our constant B. So I'm going to change that with a B. And remember that it's the constant that is multiplying to the x. And so why do we need that? Well, because to find the period, we need 2 pi over B. And so B, we found out, is a 12. And so if we divide that, we will get approximately 0.524. So far we have the amplitude, which we got from here by getting the difference of the min and the max, dividing it by 2. We also got the value for B, which we have it here. And we're using cosine because we're using the highest point as the starting point right here. So that starting point occurred at time 4, at x equals 4. So we're going to use that concept to find what we are going to call the starting or the left point. So according to our slides, we need to create an equation that will mimic the parent function. So that equation is bx minus c equals 0. For ours, we know the x value is 0, and we already know the value for b, which is coming from here, 0.524. So if I want to solve for c, what I need to do is take my 0.524 to the other side. Since it's dividing on the right, once I take it across, it's going to be multiplying. So it will be 4 times 5, 0.524. And what we will get from there, it's going to be this number that we see here on the equation, the negative 2.094. So C is equal to 4 times 0.524. And that's how we get all of our values for our equation. Sorry, I forgot to press record, so I'm going to repeat what I just said. So the third question, at least 10 feet of water for the moor to be able to dock. And so what we do here, we enter both on the calculator. It will look like this. You go to the y equals, you enter 10 to draw that horizontal line. You also enter the whole equation, which is what we have here. I'm not going to write it again. And then what we do is we press graph, and then we analyze the graph. I will show you this during the live session that we will have. And with that, we can find the intersection between those two graphs, which will be the cosine curve and the horizontal line. And so when we do that, we want to find the ones here because we want to find where the y value is 10 or greater than 10. And so we focus there. If we do that trace option or find the intersections, we will get the numbers that I have highlighted here, 14.7, and then we will get the 17.3. So I also mentioned how the time that we have from here to here, oh, I don't know what's going on. From here to here, it's also a good time because the height will be actually greater than 10 feet. And I just realized that I skipped example 3, so let's do it quickly. So we have to sketch the graph of y equals sine of x over 2. So this graph could be also written in this way. Sine of 1/2 of x, like that. So what does this tell me? The amplitude, we don't have a number, so we assume is a 1. So the amplitude is 1. That means our range is going to go from -1 to 1. Then we have this b value of 1/2, and so that helps us determine what the period is. So since b is equal to 1/2, we will calculate what is 2 pi divided by 1/2. So to do that, actually I'll need more room here. So 2 pi, we'll put a 1 on the bottom. Then we will have here 1 over 2. And if we multiply, like I've been teaching you, the sandwich rule, so that would be 2 pi over times 2 is 4 pi. And then 1 times 1 is 1. So that will, the period is equal to 4 pi. What does that mean? That it would take the graph a whole 4 pi radians to complete one cycle. So since it is sine and we don't have any horizontal shifting here, I could say that we will start at 0 for x, and then we will end at 4 pi. Why 4 pi? Because that's what we get for one period. What will be the y value of any x-intercept? 0. Now, the second x-intercept, or the one in the middle, it will be the half point between 0 and 4 pi, which will be 2 pi. It's also an x-intercept, so the y value is 0. Now, for the maximum, we take the half point between the 0 and the 2 pi, and that will equal to pi. So pi, comma, what is the maximum? Since the amplitude is 1, the maximum is 1. Finally, for the minimum, we will take the midpoint between 2 pi and 4 pi, and that will be 3 pi. What will be the minimum value? -1. So just to graph it quickly here, let's say this is 4 pi, and then we have here 2 pi. So x-intercept, x-intercept, x-intercept. Let's say this is 1, this is -1. And so we will have here at pi, we will have a maximum, and here at 3 pi, we will have a minimum point. And so the graph will look like that. And I believe we were only asked to graph one period. So yeah, that's it. This is the end of the video.